My dear students, colleagues, and all the viewers who are watching this program live from Facebook page Physics Center and School of Astrophysics and Astronomy and YouTube channel Pretam Kurdas. I'd like to welcome you all to our International Physics webinar. Good evening to you all. Hope you are well and safe from Corona pandemic. As we know that we are staying in a Corona pandemic situation, we cannot continue our normal academic program inside the campus, so we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including International Physics Webinar, and we have successfully completed our 164th International Physics Webinar. Today it's our 165th International Physics Webinar. So we are trying to adjust with this new normal situation. So today, I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Mathematical Institute of Chennai, India. And we have with us here today Dr. S. Mani sir, Adjunct Professor, Chennai Mathematical Institute, Chennai, India, and he has already connected with us. So I'd like to welcome our speaker, sir. Good evening, and thanks for accepting our invitation. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. So for those who are new, I'd like to inform that we have divided our webinar into three parts. First of all, we'd like to introduce our speaker, and then our speaker will deliver his speech, and at the end, we have a discussion session. In that time, anybody can join with us, and you can ask question by commenting also. I think you have already come to know the title of this today's International Physics webinar. Title is the Physics of Information, and our speaker is Dr. S. Mani sir, Adjunct Professor, Chennai Mathematical Institute, Chennai, India. And you can see his educational and professional experience. You can see he's completed his bachelor degree in physics from Delhi University, and he started his career as a researcher at the Indian Institute of Technology, Kanpur, and now he currently is working as an adjunct professor at the Chennai Mathematical Institute. So this is his Google Scholar ID, citation more than 600, and this is his research gate, page 30.21. So thanks for all of your patience. Now it's time to go to our speaker. Sir, thanks again for joining with us, for accepting our invitation. Sir, it's your time, sir. You can start your session, sir.
Thank you very much, Dr. Das, for this kind invitation. I feel very thrilled and very privileged to be able to talk to the Pabna place, which is in Bangladesh now. And a few days ago, Dr. Das asked me whether I have ever visited Bangladesh, but I told him no, but I have a strong connection with Bangladesh. That is, before partition, that is, it was West Bengal. And that is up to 1947, much before you people were born. You were born much later. So my father worked for the East Bengal Railway. And because the Second World War was there, we were not there during the time. I did my schooling with my grandfather, where he lived. He lived in deep South India, the southernmost part of India. So every summer we would go to East Bengal. And East Bengal, my father lived in Dhaka and also lived in what was called Chittagong. Now I think it is called Chattogram. And I remember very well taking boat rides on the rivers here in what was East Bengal, and I think I have done something which very few people in Bengal would have done now, that is play cricket in Chattogram. Mainly we were hunting for the ball because it's a very hilly place, but it was a wonderful time that we had. Thank you again for the invitation. So now I will start with the subject matter of today, and I want to start sharing my screen. Dr. Das, can I do that? Is it being shared now?
Yeah.
Hello?
Yeah, we can see. We can see your desktop.
You can see it? Is it clear?
Yeah, we can see now.
Okay. Now, I start with a very good evening to you all. and be very safe during this present conditions that we are all going through. Very unenviable condition, but that's the way it is. So now let me give you an outline of the talk. I will start with an introduction. It will give you some idea of what I have in mind. And then I will discuss the efficiency of engine, which essentially comes from laws of thermodynamics. I will be discussing the Carnos engine, which will be a revision for you. Then comes Maxwell's demon, an idea which was developed by Maxwell, and he successfully can violate the laws of thermodynamics. But that is a really strict no-no, because we all know that these laws have been tested so well everywhere, and there was a problem. This continued for 60, 70 years till Szilard resolved the problem in a way, bringing a new topic, that is of information. Incidentally, Szilard had a strong Indian connection, of course, much before partition again, but much before independence. He wanted a job in Delhi University because his fiancée was working in Jamia Millia in Delhi. And she was very staunch Christian and works as a Christian missionary. And he wanted to join Delhi University. But somehow it did not work. Instead of that, Professor D.S. Kothari joined, and I studied under D.S. Kothari, a wonderful teacher. I learned a lot of things from him, including thermodynamics. And then the Szilard resolution was not the complete story, and the story was improved upon by Landauer. Then all this, of course, was in the classical setting, but given that quantum mechanics was developed, all these things had to be put in quantum setting. This is going on for the last 50 years, and it's a very active field of research, a topic called quantum information, quantum thermodynamics, and so on. Mainly, the interests are two. One is that you are able to make smaller and smaller systems because our technology has improved vastly. The other thing is that there is some things about quantum mechanics which are not yet clear. And we would like to understand quantum mechanics better. For that, some of these methods are very useful. So now, let me proceed with the introduction, which I more or less said. In the beginning of the 19th century, engineers were trying to improve the efficiency of thermal engines. The reason for that was that the only thing that was available as a source of energy was coal. So they had to get something useful for themselves by converting coal to mechanical energy. Mechanical energy is running trains, running buses, or whatever that you want to do, or use it for military purposes. And that required an understanding of thermal emissions. And as you all know, Sadi Carnot found the maximum energy that can be extracted from thermal machines, irrespective of the substance use. This was a theoretical best thing that we could do. This is how physics proceeds. You simplify a situation, as we will see as we go along, and try to get an answer which is independent of many of the details involved. And if you are able to successfully do that, then the details can only tell you how close you can come to the ideal situation. Then he invented an engine, which we all know as Carnot engine, and other machines could at best equal its efficiency. Okay, so this is the start. This led to the second law of thermodynamics, which can be stated in several forms. I will state it in a particular form. Heat energy cannot be completely converted to mechanical energy just from one heat source. What this means is, supposing I have a heat source, energy must be conserved. That was the first law. So if I can take the thermal energy and can I convert it all into mechanical energy? The answer is no. It is not possible. When you take some energy from a heat source, you have to give back some energy to another heat source to be able to extract the energy. So it's said in a very humorous vein, the conservation of energy says you can at best break even. The second law says you will always lose. So when you try to convert heat to work. So this is the way it is. And the this idea of thermodynamics was questioned by James Clerk Maxwell, who himself has done a lot of work in statistical mechanics and kinetic theory of gases. So in 1867, James Clerk Maxwell suggested a hypothetical method to violate the second law by an intelligent person who has been nicknamed later, this was done somewhere in the beginning of the 20th century, called the Maxwell's demon. Here is Professor Maxwell, and he has been demonized here. Okay. Addressing this issue had led radically new view of information, and that has led to a quantification of information. This is the main message I want to convey, and let me stop here for a minute and explain. Supposing we were during Galileo's times or pre-Galileo, for us, momentum would not have meant anything very much. But today, momentum is a physical quantity. We all look at it as a physical quantity. Change of momentum is related to the forces acting on it. The rate of change is given by the force. These concepts originally were as foreign to us as thinking of information that is available as a source of, just like momentum is a physical quantity, information is also a physical quantity. This is the main thing which I want to convey in this talk. And this means that we should, just like we quantify momentum, momentum is mass times velocity. I mean, people could have tried different things, mass times velocity cubed, but ultimately the experiments indicated velocity times mass was what was needed for the second law. Similarly, we will have to learn how to quantify information. This is going on, and this is related, incidentally, to the entropy of the system. We will not be able to get into all the details. I will just give you a glimpse of the whole thing. And please remember again, this is the main content of the talk, that information is also a physical quantity. This talk will give an overview of all these useful developments in the last few decades. Okay, firstly, we will start revising the Carnos reversible engine. I'm sure you people have studied this in high school, and I'm sure you must have studied this in your college. So engine completes a cycle by undergoing 4 reversible operations. Remember the word reversible. The engine expands at constant temperature T1, being in thermal contact with the reservoir. So here is the reservoir, and this is in thermal contact with it. So if there is any change, any attempt to change, increase or decrease the temperature, heat will flow one way or the other. If the temperature tries to decrease, heat will flow in, so that this remains at the same temperature as the reservoir. Reservoir is much bigger than this machine, the engine, so that any change in the heat flow here is hardly going to affect the reservoir. Now, what happens is we go from 1 to 2, and this is the piston. And when I do that, the system does work for me. When it is doing, it is getting pushed this way, and I am getting work done here. This goes from 1 to 2. Now, the engine is thermally isolated. It by an insulation. You put an insulation so that heat cannot flow in or out. Adiabatic thermally isolated expansion, the engine undergoes an adiabatic expansion from 2 to 3. Again, when it is expanding, it is doing work against the atmosphere, and so we pick up that work to do various other physical interesting things for us, useful things for us. That takes me from 2 to 3. Now, the engine is in thermal contact with the reservoir at a temperature T2 less than T1. Why? Because when it expanded, adiabatically, the thing cooled down. It did work, and so it lost energy, so it cooled down. So it came to a temperature T2, and then now I compress it back so that its temperature is compressed with a heat reservoir at T2, and now this time I have to do the work. So I go from 1 to 2 isothermally, 2 to 3 adiabatically, 3 to 4 isothermally at a lower temperature. And finally, again, I put an insulation adiabatically. I take it from 4 to 1. I drew the arrow wrongly. It should have been 4 to 1. And then you see again, no, sorry, 4 should have been here, 1 should have been there, 4 to 1. Again, the work is being done by us. This process, we need to do work on the engine. So in the first 2, we get work out of the system, and the next 2, we do the work. The difference in the work is what we gain. Okay, so this is explained in the standard PV diagram. I'm exposing here pressure and volume, and I have here 1 to 2 going from here to here. This is the heat 1, isothermal, adiabatic, isothermal, back again, and this is the standard Carnos engine. I will not discuss the mathematics detail of it, but the important point is the efficiency is usually represented by a symbol eta and is given by 1 minus T2 by T1. So the efficiency is never 100% unless T2 is 0. And again, the third law says you can never get to 0. So eta is very much less than 1, usually 30%, 40%, 20%. These are the kind of things. Now, consider thermally insulated box of an ideal gas having small density and high temperature is an ideal gas. The molecules in the box execute random motion and they collide in the walls confining them. The collision is what gives you the pressure on the wall. Now insert a partition. Here it is. Here is the wall. I insert a partition here with an opening. I'm now going to describe what Maxwell did. Here is the Maxwell lemon sitting there in the green way. Now the red ones are the hot ones and the blue ones are the cold ones, the molecules. So the demon does the following. He opens the trap whenever he says the red molecule going from the side A to side B. So, but when the red molecule is trying to go the other way, he stops it. Similarly, when the blue molecule goes from B to A, he allows it. When blue molecule tries to go from A to B, he stops it. With being intelligent, he is able to do that. So this process becomes a situation like this. So all he has to do is assume these are massless and he can open it, no work is done. And this is the situation he will ultimately end up with after some time. So I will have high energy molecules here, hot ones, low energy here. So the temperature here is higher than the temperature here. This will correspond to T1 for me, and this will correspond to T2. Now notice, I can run a Carnos engine between these two. I can take a system, pick up energy from here, deposit some energy and get some work done. But what have I done in the whole thing? If I look at the whole box, I have the whole box and I have taken some energy out of it and done some useful work. That's exactly a violation of the second law that we had stated. If I look at it, the whole box, I have taken an energy out of it and converted into work. And that is exactly the violation of the second law. Whatever I just said, I've written it. I will just wait for you to read it and see whether it says the same thing for you. Okay, higher speed. The slower one is blue. So heat is now converted to work 100% efficiency by allowing the partition to move one way or the other. This violates the second law. Here I have done it in this fashion. What I can do now is I can keep a weight here. And I have here, this hot end is going to push it here, so the weight is going to go up. If the energy picked up here is just come out of this. So I have converted heat into work by a 100% efficiency. This problem was what Maxwell had stated, and several people tried to answer this problem with not too much success. Then Szilard in 1920s came out with the following resolution. He looked at a single molecule gas. He says you will just have one molecule. Then people can say, how can you apply one molecule system? It must be a statistical mechanics or thermodynamics is for large systems. So what he said was that you construct several such identical systems, n of them, and there will always be the probability that what I'm saying is right for one, but when I take it out, I will get the answer to the problem. We will see this in a little bit more detail as we go. He said the following. Resolution of the problem discussed in the previous section by considering heat engine with a system with one molecule in a box. The box is at thermal equilibrium with a reservoir at temperature T. The argument will be outlined below, led him to the conclusion, to quote his words. Now, I will give you the argument, but let me give you the final conclusion. One may reasonably assume that a measurement procedure is fundamentally associated with a certain definite entropy reduction, and that restores concordance with the second law. Here, the measurement procedure. So when he makes a measurement, we thought nothing happens, he just noted in a piece of paper. But what Zillett said is that causes the change in entropy. And that is how the second law is. Second law can also be stated that an isolated system, entropy will not decrease. It can only remain the same or increase. So what had happened in the previous case, I took out heat, so its entropy decreased. But that is not allowed by second law. But what Zillett said was the measurement procedure, when I try to write whether the molecule is on the right or the left, to keep track of it, I am spending, it causes a definite entropy reduction. This is fundamentally associated with the entropy reduction. That's what he said. This shown in the figure. Here is the figure. I have a left and a right. The demon wants to know whether it is on the right side or the left side. Supposing he finds it is to the right side, I have divided the volume V into two parts, V by 2. Then what he can do is he can put some kind of a partition here and join, as I had shown earlier, with a rope. I can put mass. So this molecule will keep hitting and try to go that side. When it goes, it will just, the weight, this will go up. Therefore, it will lose energy. That means the temperature of this will decrease. But it will pick up the energy from up there and come back to its original one. So what does it mean? I have picked up this extra work by picking up energy from the reservoir. The molecule was back to temperature T, and so nothing has happened to it. This means I successfully converted the heat from the reservoir to a thing which is going up. If the molecule were on the other side, I will just put the rope on this side and get the molecule to push me on the other side. So the demon observes the molecule and measure, and the measurement tells him which side is the molecule. If the molecule is in the right side as shown, he attaches a rope to the partition, the other end of which goes over a massless, frictionless pulley and is attached mass. It is like this, exactly what I said. And when this gets pushed up, it goes up. Temperature of this comes down, but it is in contact with the reservoir. So the reservoir supplies the heat. So what is the total audit? The reservoir lost some heat and the mass went up. So I was able to successfully convert heat into work with 100% efficiency, because this just was a spectator. It had a certain energy, it picked up the energy back. So it was the same. I am doing it the same way. Had the demon observed the molecule on the left side, he would attach the mass on this side. So Zillett conjectured that knowing which side of the box the molecule is cannot be obtained free of energy costs. He assumed energy spent in obtaining the information should match the energy from the above method, thus saving the second law. He said that if the second law has to be saved, the measurement costs that much energy that I picked up for the mass. He could not prove this result, but he said this is where the flaw is in the argument of Maxwell. Okay. It is actually easy to calculate this quantity. I will not do the calculation in front of you here. And the energy that you gain is Kb T. Kb is the Boltzmann constant. T is the temperature of the box. Log 2, this is the log to the base E of the substance. So his statement was measurement, this is the entropy which has come down. So he says the measurement caused this much entropy, kb T log 2 at temperature kb log 2, because delta Q by T is entropy. So the entropy gain is the system, when he makes a measurement, the entropy is increased by kb log 2, which takes the answer. So though we gained energy from the system, an equal amount of energy was spent in acquiring the information to make the system deliver. So now information is also entering the log book of energy. Okay. Landauer, this happened much later, around 1940s or even later, noticed a certain lacuna in Ziller's argument. And the lacuna is this. The daemon is a memory state, possesses the information in the final state. In the initial state, he did not possess it. He knew whether the particle is to the right or to the left. But initially, before observation, he did not know it. But therefore, the cycle is not complete. To complete the cycle, I must remove that information from the daemon. Only then we will go back to what is the original situation. The daemon knows nothing. There is a box which contains a molecule. He makes a measurement and then he finds out the molecule is on the right. So he has already got that information wherever he stores it. The cycle is complete, but then the information is still with him. So the cycle is considered to be incomplete till the daemon goes back to his original state. This is what Landauer said. So this means the information is stored in the memory must be erased. And how did Landau suggest a memory erasure? Okay. Okay. There is also one more comment here. Landauer could construct a physical process by which information could be stored without expending energy, as Zillard had thought, and that is, information could be stored without performing work on the system. But on the other hand, I have to remove that information to complete the cycle. That part, the erasure part, costs energy, and that change in entropy is kb log 2. This is what is called the Landauer's erasure principle. The quantitative statement is that the minimum energy required to erase one bit is 0 or 1 is kb T log 2 if the temperature. This is the energy required. We will see how this comes about in the next slide. By the way, several experiments have been carried out in the 80s, 90s to verify the Landauer's erasure principle in various different ways. Okay, now let us see. Here is the box. Let us say it is firstly in the left side. How do I erase the information? I must put it in a standard place. Here, my standard is the left side. So I have a piston and I keep pushing it here. It is here. If it is in the right by, I will push it here. So this is the standard situation. In this standard situation, I do not, now the information is erased. If this is the place where the daemon had stored the information, once the molecule, this is his material that in which he is keeping the information. Okay, now he has got it here. So he has no way to know whether this had happened for this or whether this had happened for that. So the information has been erased by taking these two and putting it into the same place. So notice it's a mapping 1, 2, and it is not a reversible map. This is what will also remind you reversible and irreversible process of thermodynamics. So in doing this, notice what has happened. When I push here, I have to do no work. But when I push here, I have to do work against this to move it here. So half the time I will do work. I can calculate the work very easily. And when you do that calculation, that exactly matches with kb log 2 times T. Okay. I have just whatever I have explained, I have put it in the slide. So let me just go through that. I will leave it for a minute and you people can read it. Okay. Now, uh, the work of Zillard and Landauer have brought a new concept that information has to be treated as a physical quantity has been debated in some quarters. Like any new ideas that come, obviously cannot be completely understood. There will be always caveats, and there are caveats, as I will finally mention a couple of them. However, the concept has been useful in understanding several experiments leading to information exchange, much like the laws of thermodynamics has been successful in understanding heat exchange. Now we come to information and quantum mechanics. New technology, we know, allows us to create very small systems of atomic dimension size. Nowadays, you are able to do that. And they obey the laws of quantum mechanics. And in the last 3 decades, many of these ideas of thermodynamics are being trying to be implemented in these areas. And many of them require, because after Landauer's work, the concepts of quantum information, and these have led to quantum computation. I will not be able to get into that in great detail, but I will give you an example in terms of a game to show how information generated using a quantum system is more efficient than the information generated in classical systems. The subject is a very vast subject, so this is only giving you a taste of what is possible. What I will show you is a way a quantum mechanical information gets transferred is more efficient in understanding certain things than a classical method of transferring information. So this is going to be the last topic that I will do. Okay, so a classical information can be thought of as being coded in bits, which takes value 0 and 1. So 5 bits is enough to create 32. 2 to the power of 5 is 32 pieces of information. So if I want to write my alphabet, I'm sure you people who are computer scientists know this. In one of the first classes, you would have learned this. And at the present day, computers where information processing takes place uses bits as basic units. In contrast, quantum systems can use quantum bits, which is commonly referred to as qubits. We discuss how a qubit functions in the next slide. A qubit is a vector in 2 dimensions and is written as a column vector A, B, where A and B are complex numbers and normalized in the following way: A squared plus B squared is 1. Now a quantum system can take values different from 1 and 0, gives enormous scope for manipulation. In the previous case, either I could get 0 or 1, but I could get different numbers. We will use the notation, what I call ket as column vector. Ket 0 and ket 1 is this kind of a column vector. These are the basis for any of these numbers. I can write AB as A times 0 plus B times 1. Okay, one can perform operations using quantum operations on quantum bit. So if I have a state vector A, I can write down minus 1 to the power A, where A is plus minus 1. If I call this plus 0 and 1, notice, so this would be, when A is 0, this becomes plus 1, and minus 1 would be the other case. I should have written A is plus 0 and 1. I've written 0 and 1 here. So this means when A is 0, this factor is 1. When A is 1, this is 1. We can also use something called a Hadamard. There are many, many operations. I needed 2, and that's why I'm doing it. Hadamard operation, which can take this state to a state like this. It's a mixture of 0 and 1. Not possible in bits. I can't have 0 and 1 at the same time. But in quantum mechanics, I'm allowed to do this. Building these systems are very important physics-wise, and people have learned how to make these kinds of transformations. So 0 goes to 0 plus 1 by root 2, and this goes to 0 minus 1 by root 2. Such a transformation is called a Hadamard transformation. Now we are ready to start the game. All right. I consider I make a suggestion to you people. Please keep a piece of paper, because I may, instead of going back and forth in slide, I will tell you exactly where you could keep a record, and it will be easier for you to follow the slides then. So keep a piece of paper. I'll wait for a minute, and then you can record what I suggest you should do in the numbers. This, not this slide, as we will see going along. Uh, Consider the following game between three persons, A, B, and C. There are 4 apples. Some number of apples are cut into half. Not all of them are cut. Some of them may be cut, some may not be cut at all, into half. And each can be given a number of half apples, which can be 0, 1, 2, 3, 4, or half integer number of apples, which is half, 3 half, 5 half, or 7 half. See, I have 4 apples. If it can be cut. Having cut, I could have been given 0 apples, half apple, 1 apple, 3 halves apple, 5 halves apple, or 7 half apples. Okay. Or also 4 apples. I didn't write that. Now, after they have started the game, they cannot communicate amongst themselves. But B and C can communicate with another person D who is conducting the game, and D will communicate the statements whatever B and C have made to A. Okay, so there are 3 persons, A and B, C, who are playing the game. D is conducting the game. When after the game starts, B and C, none of them can communicate with each other. B can communicate with D, and he can communicate with C, can communicate D, and D communicates the result, whatever they said, to A. A has to answer whether the total number of apples distributed to A, B, and C, the total number, is an even number or an odd number. This is the question. They can have, before they meet, they know that this is the situation. The game is explained to them before they start. So they can make a predetermined strategy for communicating to A, of course through D, so that A can make a decision. This is the situation. Okay. Now, one classical strategy could be the following. Notice we need to consider only the case of 2 apples, as increasing 2 to 4 is just an addition of 2. When I add 2, the evenness or the oddness will not change. So that was just to confuse us that the game has been made into a little bit more complicated one. I can easily simplify it by just looking at it up to 2. Okay, since A knows his or her apple, we need to consider the 16 possibilities of distribution of B and C. Half the possibilities will be integer, the other half will be half integer, because A can have full integer and B can, by the way, the total number that is distributed is an integer. The question that A has to answer is the total number an even number or an odd number. Okay. For example, the distribution could be half with A, half with B, 0 with C. This would correspond to a total of odd number. Otherwise, it could have been 1 with A, 1 with B, 0 with C. This is 2. This would be an even number, and so on. Now, half the possibility would be an integer. The other half would be half integer. Again, knowing his or her number can decide to distinguish. If A has half number, then he knows the sum of B plus C must be half, because the total number is full. And if A had a whole number, B and C would have been whole. So that's the situation. Assume A has a whole number of apples. If A has 0, B and C can have 6 possibilities. Notice B plus C must add up to 1 or 2, right? 0, 0 is possibility. Half, half is a possibility. 1, 0, 0, 1, 3 half, 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 3 half. So this is the 6 possibilities he can have. If A has 1, we have 4 possibilities. 0, 0, 1, 0, 1, 0, half, 3 half. Okay, these are the possibilities. And of course, the other one, 3 half will not make any difference. It's the same story there. If A is half, then there are again 4 possibilities: 0 half, half 0, half 1, and 1 and half. Here also 3 possibilities: half 0, 0 half, 2 possibilities. Okay. So the possibilities add up to 2 plus 4 plus 4, 10 plus 6 possibilities. Assume it was decided. Now this is the thing which you people should note down in your paper. Assume that it was decided that B will have his flag raised up if the number is half or 0. That is, B will raise the flag if it is half or 0, and it will be down. This is the communication B will give D. So D will tell A, B's flag is up or down. So this is the information: half or 0, flag up; 1, 3 half is down. C will have flag raised up when it is half and 1, and down when it's 0 and 3 halves. Now we have the following possibilities. We can have, if BC is 0, 0, flag is up. Now notice, BC is 0, 0, flag is up and down. If it is 1, 1, it is down and up. Both cases, when I add the two, the number is even. This is assuming A has whole number of apples. Okay. Assume the A has whole number of apples. That's what we are considering. So B and C should have whole number of apples. Now, if it is 0, 0, the flag is up and down. If it is 1, 1, it is both this much. Okay. If BC is 0, 1, then both flags will be up, and if it is 1, 0, both flags will be down. Again, now notice here, if it is both flags are up, it will know it is an odd number in the hands of those people. So given that, the total number is an odd number, and he knows this is the answer. Okay. Similar analysis can be done when B and C each hold half integer number of apples. Again, he can guess correctly the answer. Now consider when B and C correct answer. Okay, analysis. It turns out A can make a correct decision only half the number of times. Let's see why. Now consider the case when BC is half 0 apple, in which the flags will be up, down. But this signal could also come from 0, 3 by 2. So if A has half, half plus half will be 1, half plus 3 half will be 2. So in the one case it will be odd, in the other case it will be even. Let me repeat. Now A has half number of apples. Supposing B has half 0, he will have up, down. If BC has 0, 3 half, again it will be down, up. So it will not make any difference. The total will be, in one case it will be even, and the other case it will be odd, and A cannot make up her mind, or his or her mind, on the evenness of the total number of apples. The person has to make a guess. When he makes a guess, he gets it right only 50% of the time. So we can try this with different kind of strategies, and there is a mathematical proof that the best that classical strategy can give is 75% success in all this. This is the maximum that a classical strategy can give. Now let us do with 3 qubits. Here a certain explanation is called for, and let me explain. We start with ABC possessing qubits. This kind of a qubit was made originally in some place, and A got a qubit, B got a qubit, and C got a qubit. They took it there. But it is a collective wave function which is given by this expression which is there. Note that such a state is a superposition of classically different states, which is such a state is not possible to obtain classically. To actually experimentally construct the state is not an easy task, but it has been done. Okay, Now, each of them, having taken their qubit, can only operate on their qubit. They cannot operate on B and C. B and C are far away. So A can perform the operation on its one by this, and this one by -1 to the power of xa, where xa is the number of apples A possesses. A incidentally could possess half number, so this will be -1 to the power half, and that will be I. Okay, B and C can perform exactly the same operation on one on their qubits. So what will happen to the new state? This is the state. I will get here -1 to the power of xa, -1 to the power of xb, -1 to the power of xc. So the state will become 0a, 0b, 0c, plus -1 to the power of xa plus xb plus xc, this expression. But xa plus xb plus xc is the total number of apples A, B, and C have. So if it is even, it will be plus. If it is odd, it will be minus. So using this operation of taking 1 to -1 to the power of xa being the number of apples, we get this answer. Okay, so that's the situation. Now, to each of them, each of the person applies a Hadamard operation. 0, 1 by root 2, 0, 1 minus 1 to 1 minus root 2 on their respective qubits. So this becomes 0, 0a plus. Okay. How you do it is you have to multiply all three of them. And when you do that, after the calculation, it's straightforward to do it. You will find that if there is a minus sign, two of them should become plus, otherwise they will cancel. And so this is the situation for the plus sign. For psi plus, this is the answer. Now, use the pre-agreed convention. B or C will raise the flag up if their qubit is in the state 0 or 1. Now let's look at it. B and C, for this, it will be 0, 0, will be up and down if it is 1. So in this case, if it is A has 0, and in this case, it will be 0, 0 means it will be even. If it is 1, it will be 0 to odd, if this is the case. On the other hand, if it were this, you can add up all that. Minus sign, remember, will give me, so I will get 1 up, 1 down, 1 up, 1 down here. And if A had odd, it will be 2 down, 2 up and 2 down. Just the opposite of here. If A had 0, it would have been up, up. A had 1, it would have been up, down, down, up. If here, it would have been just the opposite. If A had 0, it would have been down, up. So here, the number of is xa plus xb plus xc is 1. Here, xa plus xb plus xc is c. So this will give you the number of odd, apples as odd. And so the logic is this. A looks at the number of apples he or she has. Then it sees whether it is up, up or up, down. Then if it is up, up and up, down, it knows it's even. And if it is odd number she has, and if it is up, down and down, up, again, she knows it is even. Or just the opposite for this. So this way, quantum processing gives you information 100% of the time. This is the answer. I have been a little fast. I will share the slide with Dr. Das. Any of you who are interested can go through this calculation more carefully. But given the time, I didn't want to. I just wanted to give you a taste of what quantum information, quantum algorithms like this can give rise to, give you a different taste. More recently, a general analysis has been carried out by Ueda and Sakawa. This is in archive. This is published in 2008, showing that the energy cost occurs both in measurement and erasure. That depends upon how you do it. But when I add the two, that will add up to kT log 2. So it depends on how you proceed to do the measurement and do the erasure of the measurement. That's it. A very nice simplified article, L is missing, is written by Paul and A.M. Janavar in explaining the work Janavar Paul is 1 and 2, Jennifer is 2, a second author explaining this work of Ueda and Sakawa. So the thing has taken a swing. Zillett said measurements cost energy. Landauer said erasure of measurements cost energy. These people say, wait, it depends upon how you make the measurement, how do you make the energy, the erasure, and the work which they have done, which is explained in Paul and Janauer beautifully, is a very simple exercise which any student who has had undergraduate training can follow it and clearly understand why this happens. So it's somewhere in between. Now, let me just summarize. The information has to be treated physically, and it's a physical source, just like energy is. Quantum process of information can yield more information than classical process. The subject encompasses several areas: quantum thermodynamics, open quantum system, quantum cryptology, to name a few. Very exciting dates lies ahead, and that's the answer. Thank you very much for your attention, and I close the talk by now.
Thank you, sir, for your wonderful presentation, sir. I think students have learned a lot of things about physics information that you have explained. So we have got 2 questions in the inbox. So if you allow, we can start our discussion session.
Let me see the questions. It will be in the chat box.
Yeah, I can send you in chat box. You can see.
I would like to see it in the box. Where is it? Here it is. Oh, what is Maxwell Demon? How do quantum computer help us? Maxwell Demon is an imaginary character that we had built to see. In physics, we do this several times, right? When we talk about special theory of relativity, there is an observer in one frame, there is an observer moving with constant speed. These are things just to keep the picture clear. So similarly, Maxwell's demon would be some kind of an apparatus which will be able to find the speed of a particle and then apply a trap, which will be again a mechanical device in which once it measures the speed, the trap has to open and go. And this kind of a mechanical device can be made. And this is what the experimentalists do all the time, right? So that is what is the Maxwell's demon. And how do quantum computers help us? Quantum computers are not yet completely built, at least they are not yet out in the market to the big level. Right now, there are many problems which can be solved by quantum computers, mathematically done at a much faster speed than classical computers. There are many things. So it is in those situations that a quantum computer will be helpful.
Thank you very much, sir. Thanks again, sir, for accepting our invitation, sir. As we don't have any more questions, we should conclude our discussion session, sir. And we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. As the video will remain in Facebook and YouTube, if anybody will ask question later, so I'll
communicate with you. Welcome, most welcome.
Thank you, sir.
Thank you very much for this opportunity, and especially
of course, after the COVID, I'll definitely invite you to rewind your memories that you have passed in before maybe the separation. So thanks, sir.
Thank you very much. Wonderful. Bye.
Good night.